Hello, my name is Victor Cola and I'm going to share with you some of the results of our modeling study concerning the human skin epidermal thickness influence on penetration depth for detected photon in a spatially resolved diffuse reflectance spectroscopy device. Optical biopsy refers to spectroimaging techniques developed to characterize biological tissue optical properties. It differs from conventional biopsy by its non-invasive nature. The data analysis challenge consists in extracting from the measured intensity spectra discriminant information related to the characteristic and concentration of elements like absorbers, diffusers, and fluorophores. They are valuable information to determine the nature of the tissue. Optical biopsy is involved in the perioperative support of the removal of cutaneous carcinoma. Indeed, its use makes it possible, on the one hand, to improve the efficiency of diagnosis and, on the other hand, to establish surgical margin. Several point spectroscopy techniques have already proved to be effective for cutaneous carcinoma in vivo diagnosis. This includes Raman, exogenous and endogenous fluorescence, or diffuse reflectance spectroscopy. In addition, it's also possible to enter several source sensor distances. This is called spatially resolved spectroscopy. It allows to probe different depths. In this context, our lab has designed a spatially resolved device for optical biopsy. This lab is called Spectroscopy and is currently used in a clinical study. Its optical probe is made of a central source fiber of radius 300 micrometers, delivering white light illumination to the tissue in contact, and of 24 detection fibers of radius 200 micrometers, equally distributed on 4 concentric circles corresponding to the 4 source sensors distances. Those distances are spread between 400 and 1000 micrometers with a step of 200 micrometers. Diffuse reflectance and autofluorescence spectra are acquired and subsequently exploited to design a real-time device able of establishing surgical margins. For this study, we will only focus on diffuse reflectance modality. In parallel, a photon progression algorithm has been adapted to get diffuse reflectance simulated spectra with conditions mimicking the clinical probe's configuration. The ambition is to use this simulation for the estimation of diagnostically relevant optical parameters from in vivo diffuse reflectance clinical spectra. Indeed, the evolution of optical parameters for each layer around the lesion can be linked to the tissue pathological state. The skin layer optical parameters will be obtained by solving the inverse problem, where simulated spectra result from the adaptation of the photon transport code. The elements introduced so far make it possible to situate the work undertaken. If you want to estimate the optical properties of the layer K, we have to be sure that the diffuse reflectance spectral region we are analyzing consists of photons that reached the layer of study. As indicated in a very symbolic way here, it's a question of determining the sensitivity for a couple, wavelength, source sensor distance, to each layer. In other words, it's a question of providing numerical evidence that a photon at a given wavelength and detected at a given distance is likely to carry the information characteristic of the tissue layer. Considering that the thickness of the epidermis, made of stratum corneum and living epidermis, varies significantly with body location, this study has to be led for several epidermal thicknesses. That's why the result presented here can provide useful tools during the design of an optical biopsy device, and secondly, it can facilitate the development of an elliptical photon propagation model that enables inverse estimation of relevant optical parameters from in vivo spatially resolved diffuse reflectance spectra. The accuracy of the experiment is based on two things. The first is the correspondence between the geometrical configuration of the real clinical probe and the simulation one, while the second is the design of a realistic numerical skin model. For this purpose, a 5-layer skin median was implemented, representing from superficial to deepest layer the stratum corneum, the living epidermis, the papillodermis, the reticular dermis, and the subcutaneous fat. To consider the epidermal thickness variation between body sites, we choose to offer 3 media corresponding respectively to a thin, a median, and the sig value of the epidermal thickness, made of stratum corneum and living in epidermis in our model. For the optical behavior, and more precisely the absorption, only 5 chromophores were considered, namely blood, water, melanin, lipids, and beta-carotene. The figure on the right shows the contribution of pure chromophore absorption. The final absorption coefficient of a layer is then deduced as a weight sum of pure absorption coefficient, where the weight are the volume fraction of the chromophore in that layer. For the scattering coefficient, this can be divided into a contribution from blood and a bloodless base scattering component. Both are presented on the figure. The contribution of a blood is then multiplied by two factors. The first is the volume fraction of the blood, while the second takes into account the mean blood vessel diameter in the considered layer. By applying the formula described in the previous slides, we finally obtain the absorption and scattering coefficients of each of our 5 layers. The presence of hemoglobin absorption peaks in the irrigated layer can be noticed, as well as the diffusion barrier of the stratum corneum. Refractive index and anisotropy factor were considered wavelength independent. Let me now present our simulations code. It's a GPU Monte Carlo code that we adapted to fit our Spectrolife clinical device. The medium where photon travel is constituted of layers which are described by their thickness, their absorption and scattering coefficient, their refractive index, and their anisotropy factor. The update of photon position in the layer K is done according to this expression, while its new direction is calculated according to any Grunstein phase function. The absorption is managed by weight loss along the optical path, while diopter managements obey to Snell-Descartes law. Finally, photon death is considered when it escapes from medium or the time of flight of weight threshold is reached. To match our clinical device, we had to complete the existing code to integrate the spatial resolution. Photon contribute to spectrum signal associated to a given distance only if it satisfies collection geometric condition. The technical features of the simulation configuration are summed here. To acquire a spectra, 100 million of photons were sent to each of the 81 wavelengths between 365 and 765 nanometers, corresponding to a computation time in the order of 1000 seconds. From the code described so far, tools to characterize the depth behavior of the detected photon have been created for fixed wavelengths and fixed source sensor distance. It's the case of trajectory maps that are obtained from a radial revolution around the z-axis. Black and purple surfaces represent the source fibers and the detection areas on the top of the skin volume. When a photon is detected, it consists in incrementing the position where scattering event happen by its final weight. The second numerical tool is the maximum probe depth histogram. For a detected photon, it consists in storing its maximal depth and incrementing the occurrence associated to its depth by the photon final weight. Before studying the depth penetration with epidermal thickness variation, we firstly present here the result for the mean thickness medium, which corresponds to a stratum corneum of 20 and a living epidermis of 90 micrometers. Black and purple square respectively represent the source and the detection fiber, while black horizontal lines show the diopter position. The trajectory maps illustrate the impact of wavelengths on penetration of the detected photon when the source detector distance is fixed at 1000 micrometers. One can notice that the strong absorption capacity of hemoglobin at 450 nanometers is responsive for superficial trajectory, whereas the lower optical opacity at 550 nanometers allow for deeper ones. Concerning the source to detector distance impact, we can notice that great distances is associated with deeper trajectories. Also, we can observe the typical path between source fiber and detection fiber called banana shape. Similarly, it's possible to study the dependence of the wavelengths on probe depth histogram. The abscissa corresponds to depth probe in micrometers, while the ordinate is for the occurrence expressed in percentage. Here again, Black vertical lines refer to diopter position, while dashed dotted lines and continuous purple line represent the quartile and median values. The colored area under the histograms between the two quartiles then represent 50% of the total areas. In other words, half of the photons contributing to the signal at this wavelength have reached at most a depth between the first and the third quartile values. One can notice the presence of abrupt transition at diopter positions corresponding to reflection and caused by the refractive index mismatch between two consecutive layers. The shift of the histogram toward greater depths clearly appears when the wavelengths vary from near UV to near IR, excepted in the hemoglobin absorption peak. At fixed wavelengths, it's also possible to visualize the source sensor distance impact on histograms. The graph conventions are still the same. We can notice that photons go deeper, as well as the widening of the probed volume visible here in the form of the interquartile enlargement for longer distances than the shorter ones. Since all the histograms are available for each short detector distances and for all emitted wavelengths, it was chosen to synthesize the spectral penetration behavior of the detected photon by extracting the median and the quartile for every couple. The results obtained from this calculation are presented here with the same graphical convention. The quasi-linearity on the probed depth can be seen as a function of the two varying parameters, excepted in the first hemoglobin absorption peak at 415 nanometers. More importantly, it can be noticed that the spatial resolution and the spectral range of the device allow to probe depths from 50 to 1050 micrometers. Moreover, one can read there that the photon having contributed to the fourth distances spectrum and for which lambda is greater than 450 nanometers have largely visited at most the reticular dermis layer. On the other hand, it is visible that the photon of the first distance and for which lambda is lower than 400 nanometers stayed globally confined in the stratum corneum and the living epidermis layer. Finally, one can also observe that the interquartile range widens when lambda is increasing, and this for all the source to detector distance. Indeed, the probe volume is very localized for the near UV wavelengths and spreads when it approaches from the near ones. Now, we will study the impact of the thickness of the epidermis on the diffuse reflectance spectra and on the probe depth. We begin by providing here the evolution of diffuse reflectance spectra for thin, intermediate, and thick epidermis. One can note for the first distance that the hemoglobin signature at 415 nanometers is less visible for thick media. Photons less penetrate irrigated layer due to optical epidermal barrier. Moreover, one can see an inversion between D1 and D4 in the signal amplitude. Let us try to explain this behavior by analyzing depth penetration in every of the three media. Those four figures illustrate the depth penetration at each short to detector distances for the thin, intermediate, and thick epidermis. The three bars on each figure show the diopter's position for the three different configurations. For the sake of clarity, the area between quartiles is no longer colored, but dashed and continuous lines still represent quartiles and median values. The color code allows the association of the curve with the three media. If you observe the probe depths at D1 for the thickest epidermis model, we notice that most of the photons having contributed remain confined in the stratum corneum and living epidermis layers. For the thinnest epidermis model, the photons have largely visited the papillodermis layer and even the reticular dermis one, especially for the near IR wavelengths. The evolution of the spectra at the third distance for the different thicknesses may be explained by the high scattering capacity of stratum corneum and living epidermal layer at the origin of a short path length return of many photons to the surface and thus captured at D1. If we now consider D4, the figure of the probe depth showed that, in general, the increase of the source detector distance forces the photon to dive into the depths of the medium. The superficial backscattering effect is no longer observed. The refinement of the stratum corneum and living epidermis layers allows the photon to penetrate deeper into the reticular dermis. The resulting optical path is then more consequent, which could explain the decrease of signal with the thickening of the skin. The photon propagation distance D2 and D3 will then correspond to a transitional state between these two modes. Let's now discuss the limit of the experiment presented here, and let me present you the further work associated with this presentation. A skin model was followed taking into account the 5 main chromophores of human skin. However, the latter does not consider the phototypes expressed in the model by the volume fraction of melanin in the living epidermis. In addition, the media considered here were healthy. It would be judicious to apply a similar approach with a skin model presenting carcinoma. Subsequently, we plan to find a decomposition of the diffuse reflectance signal by layer contribution, which could allow to design a cost function and an estimation algorithm adapted to the layer geometry of skin. The technique thus created will allow the estimation of optical properties by solving the inverse problem, firstly from numerical spectra, then from real spectral live acquisition on optical phantoms, and, in the long term, from clinical spectra. To conclude, we designed a 5-layer numerical medium that takes into consideration absorption and scattering properties from the main human skin chromophores. We then adapted a Monte Carlo code in order to fit our spectralized device, making the acquisition of simulated diffuse reflectance spectra possible. We then used the simulation to obtain the numerical information concerning the behavior of photons in depth. Qualitative tools like trajectory map have been applied, and the exploitation of quantitative histogram allowed to link the wavelengths and the source to sensor distance to the probe depth. We finally analyzed the evolution of the diffuse reflectance spectra with the widening or the narrowing of the epidermis to mimic the displacement of the probe on several body locations by using the implemented numerical tools. Those simulations allow us to learn more about the behavior of photons detected in depth and thus allow for a better interpretation of the simulated and measured diffuse reflectance signals. This information will be used to better apprehend the diagnostically relevant estimation of optical properties by the inverse problem solving. With that, I would like to thank you for your listening, and I'm looking forward to receive your questions.